Alright, so let's say we want to find the total mechanical energy for an object in orbit with the sun. Well, it's kind of simple because what you could say, or what you would write, is that the total energy, total mechanical energy, would equal all the kinetic energy that the planet, or the satellite, or whatever is orbiting the sun has, plus the potential energy between them. So then plug in, your equations, 1/2 mv squared minus gm over r being the orbital radius of the orbit, right, the distance between the sun and the satellite or the planet. Let's say we don't want the velocity in the equation. Let's say we're trying to simplify this without velocity. What you can do is use our F-net equations, because we know that the centripetal net force is going to be Fg, right? So you could do that Fg is the centripetal net force, which is equal to mv squared over r, and then you can just plug in your Fg equations, gm1, m2 over r squared. So the big M is the mass of the sun, little m is the mass of the satellite, and hey, there's a mass and satellite in both sides. There's also the r. These are the same r in this case, right? Because r is the orbital radius, which also is the distance between the sun and the satellite. So you can actually get rid of one of these r's, and then this is r squared. So we still got to keep that there. And then, yeah, you're left with gm over r is equal to v squared. You can take the square root, and you can get like the v is equal to square root gm over r, but there's a v squared here, v squared here, so I don't even have to like do that. I can just substitute that here and get 1/2 m gm over r minus gm over r. So this is the same as g big M little m over 2r minus gm over r. So then if you plug in a 2 here, right, if you're same denominator because we're doing fraction math, get 2 on both sides, you will get negative, I read the little m, oops, negative g m over 2r. So this is the total mechanical energy of an object in circular motion with the sun. So how can we do the same thing for an elliptical orbit, right? Let's say we have an elliptical orbit with the sun, which is way more common. A lot more planets have elliptical orbits. It's actually Kepler's first law. How can we actually figure out how can we figure out the E total? Because we can still do the same process with E total equals 1/2 mv squared minus gm over r. But it gets a lot harder because we don't want velocity in here. If we're going to try to simplify this, how are we going to go about doing that? Well, the key here is conservation of angular momentum. So in both of these orbits, angular momentum is conserved, and just as a reminder, I'll write it here, that angular momentum is going to equal I, your rotational inertia, times omega. For a point mass, you have mr squared, and then omega is v over r, so you actually get that angular momentum is equal to mvr for a point mass. So in both cases, angular momentum is conserved, which is pretty obvious here because, mvr, v is constant the entire time. But it's a little less obvious here because obviously it's going to kind of slow down as it gets far away and then speed up because the force is going to accelerate it, and then it's going to accelerate it and slow it down, speed it up, slow it down. So v is changing, but then r also changes to balance it out, right? If your distance from the sun decreases or increases by 2, your speed is going to increase, well, it's going to change by 1/2, right, to kind of balance it out. So angular momentum is conserved. There's no outside torque by the sun because everything is parallel and stuff. So the angular momentum here, let's say we have a mass going here at a speed of v1, and then this is at a speed of v2. This is the closest distance to the sun. We call it perihelion. This is the farthest distance from the sun. We call it aphelion. So I'll actually just say E total is going to equal v1 r1, but remember, energy is also conserved. So the E total here is going to equal the E total here. So you could really have v2 or whatever, as long as v1 r1 or v2 r2, right? v1 r2 the distance is r1, so just be careful about that. But angular momentum is also conserved, so we'll say that the mass times v1 times r1 is going to equal m times v2 times r2. We need an equation to figure out v1, but I don't really, have, we can't use a centripetal equation because it's not in uniform circular motion. So we could just use energy, right? Or we can use angular momentum to figure out that, okay, v1, v2, okay, so actually let's do this. M's cancel out, and then we get v1 r1 over r2 is equal to v2. So that's an equation for v2 in terms of v1, but I don't want v1 at all, right? If I plug this into here, right, and I change this to r2 and stuff like that, it's not going to be fun. So what we're going to, because we still have a velocity in there, what we can do is we can actually use conservation of energy, like I was kind of talking about, and we can solve for velocity like that and plug it in, hopefully get rid of the v term, and we can get our equation. So let's do this. The energy here is going to equal the energy here, so 1/2, I'm just doing k plus u, k initial plus ug initial equals k final plus ug final. Actually, I'll just write that just so it's clear as day. I don't want this to be confusing. So 1/2 m v1 squared minus, right, because we have negative ug, m over r1, not initial, just r1, equals 1/2 m v2 squared minus gm1 m2 over r2. So now I already solved for v2, right, in terms of v1, so that gets rid of like sort of my one unknown, right, because I don't want two velocities in here. The whole goal is to have no velocity. I don't want to have to deal with two, so I can just take this v2 and plug this in for v2 essentially. So I'll just rewrite everything. 1/2 m v1 squared minus g m over r1 is going to equal 1/2 m. Then we're going to plug in v1 r1 over r2 squared minus g m 1 m2 over r2. Okay. So still looks pretty nasty. Nice thing is we can drop out all these m's because as flippant physics like to say, everyone invited the m. And then we can drop out little m. Big M, which represents the mass of the sun, we still want in there. Not everyone invited big M. We can't just cancel it all out. So we're really left with 1/2 v1 squared minus gm over r1 equals 1/2. Now I have a v1 squared r1 squared over r2 squared, right? Because I'm just squaring everything in there. And then we're going to subtract it by gm over r2. All right, I want to solve for v1, so I got to get all my v1s on the same side, and I want everything else I really want on the other side, right? Because it's algebra, we're just solving for v1 here. So let's actually go ahead and subtract this onto this side. So 1/2 v1 squared minus 1/2 v1 squared r1 squared over r2 squared is going to equal, so I'm going to add, now I want everything else on the other side, so I'm going to add this term, gm over r1, to both sides. So I get gm over r1 minus gm over r2. Alright, so this looks a little bit cleaner. In fact, on this side we have a 1/2 v1 squared for both these terms, so we can just factor it out. So we get, I messed up somewhere. Did I mess up somewhere? No, I didn't mess up somewhere. Did I mess up somewhere? Oh no, I didn't. Okay, sorry. I did this in the morning and I realized I did it differently. So no worries. We're doing everything fine. 1/2 v1 squared 1 minus r1 squared over r2 squared is going to equal. Okay, let's actually do the fraction math here, right? We want these to be common denominators, so we got to multiply this one by r1 over r1, and to have this to have the common denominator of r2 times r1, you got to multiply this by r2. Fraction math is sometimes not fun, but you got to do it. And now that they have a common denominator, we can just do our usual gm r2 minus gm r1 over r1 r2. So couple things we can do to clean this up. because remember, at the end of the day, we're solving for V1. We could say we can do this. We could do this similar thing here, where okay, 1 is the same. We want to subtract this, so we can change this to r2 squared over r2 squared, right? Because that's the same thing as 1. So then you're left with 1/2 v1 squared r2 squared minus r1 squared over r2 squared. So as you probably figure, this is just a lot of math. As you know, the physics is here, but now it's just algebra. Okay, so this looks good. Then we can actually just factor out gm over r2 minus r1 over r1 r2. So yeah, now this is kind of getting somewhere. This is a fraction, so if we want to get rid of this fraction on this side, because we're isolating v1 squared, you can multiply by the reciprocal. So we can just multiply by the reciprocal. Sorry, we can just multiply by the reciprocal here, multiply by the reciprocal here. So the reciprocal of that is r2 squared over. Now here's what I'm going to do. If you remember from algebra 2 way back then, r2 squared minus r1 squared, you're subtracting the two squares. That's difference of squares. So the difference of squares formula, right? A squared minus b squared, a plus b times a minus b. We can do the r2 minus r1. Oh, I can't write like this. Sorry, I'm gonna make this just fit neater. r2 squared over. Now I'm gonna do difference of squares. r2 minus r1 over r2 plus r1. Okay. So, just to kind of recap, we just multiply by the reciprocal in order to get rid of the fraction, right? I'm isolating v1 squared, so I'm going to be left with 1/2 v1 squared, okay? And then, now, yeah, took care of that fraction, but on this side, we can simplify a little bit, because we have an r2 here, r2 squared over r2, right? So, I'm going to have gm. I don't have to do r2 squared, I just have to do r2, because this cancels out, so I can get rid of one of those. So let me just write this a little bit nicer. We'll say 1/2 v1 squared is going to equal gm r2, right, because we still have that r2. Now this is why I did difference of squares, right, because r2 minus r1, we have an r2 minus r1 term right here. That actually just cancels out completely. Right? So on the bottom, now you're going to be left with r1 times r1, r2 plus r1. Now, what we can do is we can actually just multiply both sides by 2 to get rid of that 1/2. So we're left with v1 squared equals 2gm r2 over r1 r2 plus r1. Phew! That actually simplified pretty nicely. We actually got something like, you just kind of, I'll just draw blocks around this. So that's pretty cool. Now one thing to keep in mind is that this r2 plus r1, if we come back to our diagram here, you can see r2 plus r1, that's like the entire sort of major axis of the ellipse, right? It's the entire line here, right, when you add them up. So if the semi-major, the major axis is like the diameter of a circle, right, at the half, if you're kind of split in half, that length is the major axis. So the radius is half the diameter. Our semi-major axis is going to be sort of, if I were to split the ellipse like this is what we call the semi-major axis. We call it A. So R1 plus R2, right, it adds up to 2A. We can actually just substitute in 2A right here. So it simplifies even nicer. And then we have a 2A we're going to have here. There's a 2 on top of here. We can actually just cancel out the 2. So this actually simplifies very nicely to, oh my god, this is kind of, okay, don't use your fingers, guys. Don't just use the eraser, you know, it's just better in the long run. We're left with v1 squared equals gm r2 over r1 times a being the semi-major axis. So, yeah, cool stuff. We have this we have this v1 squared. We can take the square root, once again, v1 equals square root gm r2 over r1a, but we have well, at the end of the day, we're trying to find E total, so we can just take this whole thing and substitute it back in there, or not here, here. So E total equals 1/2 m gm over r2, or r2 over r1 times a minus gm little m over r1. Okay, we're getting to the end of the road here. We just got to now do some more fraction math. I'm not going to do this. I'm not going to write E total for each thing, but it's just fraction math from here. So m I can put on the denominator, so gm little m over r2, and then I have 2 r1a, so 1/2, I can just put 2 in the denominator, same thing, and then I have r1 times 2a. So this is back to kind of what we had here, with the 2a being the total major axis. So we're still subtracting by g m1 m2 over r1. All we got to do now is just plug in a 2, or multiply both the numerator and the denominator by 2a. We're trying to get that sort of what's the word called? Common denominator. Yeah, so we can do the fraction math. So in the end, when it's all, you know, I'm going to try to draw this a bit lower actually, but when it's all done and settled, as the kids say these days, we're going to be left with g big M little m r2 minus g big M little m over 2a. So over 2a r1. So last thing we can do, I mean technically this is done, but to simplify it even further, you can factor out the gm little m r2 minus 2a over r1 2a. Now to finish this all up, remember 2a is equal to r1. I thought I wrote it down somewhere. It's okay. It's equal to it's equal to r1 plus r2. So now I can just plug it back in here. We're almost done, I promise. I know I've been kind of saying that. Minus r1 plus r2 over r1 2a. Now, the last thing we can do is, right, this is the same thing as just subtracting, you know, minus r1 minus r2. This r2 cancels out here, so you're left with negative gm little m r1 over r1 2a, and we have an r1 in the denominator. So at the end, when it's all done and settled, I have to crouch down for this. This is how important this is to me. E total is going to equal negative gm little m over 2a. So that's pretty cool. That is pretty cool. Now, if you're in a circular orbit, A is kind of just R, right, the semi-major axis, so you're just left with this equation right here. But even for something like in an elliptical orbit where it's not circular, if you have that, you know, semi-major axis, that major axis, this will be the E total. So that's a pretty cool thing to note. If you ever find an object with this much energy, it's in an elliptical orbit. So yeah, thank you for watching. I know this was kind of a long video. Stay tuned for more stupid videos, I guess.